Welcome to this tutorial. I'm solving question number 10 of paper 21 October-November exam series of 2021 in this tutorial. The topic of this question is half-life. The question says the isotope yttrium-90 Y9039 is radioactive. It is a beta particle emitter. So it is a very important information about the radioactive substance that decays to product Q. The product Q is stable. Part A state one feature that is common to all isotopes of yttrium. So the common feature could be stated as they have same number of protons. All the isotopes of an element have same number of protons. Describe how a neutral atom of Q differs from a neutral atom of yttrium. Since product Q is being formed when yttrium is undergoing a beta decay, so let me write the equation first. We are starting with yttrium 3990. When it undergoes a beta decay, it emits a beta particle whose charge number is -1 and mass is 0, and a product Q is formed. Now in a beta decay, we know that a neutron from the yttrium would be converting itself into a proton and an electron. This electron would be emitted from the nucleus, but the proton remains a part of the nucleus. So as a result, the proton number increases by 1, but the nucleon number remains the same. Although the nucleon number remains the same, but the composition here is different. For Y or yttrium, we have 39 protons and 51 neutrons here, while for Q we have 40 protons and 50 neutrons. So using all this information, we can write the answer for this part. So we have to describe how a neutral atom of Q differs from a neutral atom of yttrium-90. So it has, the first thing is it has one more proton and one more electron as compared to yttrium, while Q has one fewer neutron as compared to yttrium. So the number of protons for Q are 40, one is greater than yttrium, and the number of neutron is 50, one fewer than of yttrium. And the number of protons, electrons are same for a neutral atom. So the number of electrons are going to be equal to the number of proton in a neutral atom of Q. Next part says a sample of yttrium is placed close to a radiation detector in a laboratory. There are no other radioactive samples in the laboratory. A counter records the count rate. Figure 10.1 is a graph of the count rate plotted against time. So we have the count rate, counts per minute here on the y-axis, and we have time in hours on the x-axis. So from this figure, the first task is we have to use this figure to determine the average background count rate. Now from this figure, we can see that the count rate is starting at a value of 70, 72, 74. So it is starting around 74 and then it is decreasing. But we can see after reaching a certain value here, the count rate is not decreasing further. It has become constant. So if we take this value, it becomes equal to 18 on the y-axis. So the background count rate is the value obtained from the half-life curve. It is the value after which the curve does not decrease further. So when the exponential decay of the curve stops and the curve becomes constant or horizontal, that gives us the background count rate. So from this graph, we can say that average background count rate is 18 counts per minute. Now the next part says suggest two different origins for the background count rate. So one could be rocks. They contain the radioactive material, so they emit radiations. And secondly, we could say that cosmic rays could be another source of background count. Using figure 10.1, determine the half-life of yttrium-90. Show how the answer is obtained. So from that graph, we have to find the half-life. We can see that the initial value for the count rate is 74. We have already found the background count rate, which was 18. So I'm writing here first the initial count rate would be equal to, when we subtract the average background radiation, it is 56 counts per minute. Okay, now the next thing is, we know that after one half-life the count rate is going to decrease by half. So after first half-life it would become 28, while on the graph, since the average value of background count rate would be added to this value, so on the graph it would be equal to 46 counts per minute. Okay, after the second half-life, the 28 would again be halved and it would become equal to 14, while on the graph the value taken should be 14 plus the average background count rate, so it would be equal to 32 counts per minute. Now continuing in the same manner, the next point is when we have after third half-life, the count rate would further decrease by half and it would become 7, and on the graph we have the value of 7 plus 18 equal to 25 counts per minute. So this is the third value that we have obtained here. The first one is the initial one here. After first half-life it becomes 46 on the graph. After second half-life it becomes 32. After third half-life it becomes 25. Now we would consider these points on the graph and find out what is the value of time in hours against these count rates. So the first one is 46, and 46 is indicated by this line. This is the 46, and if I match this line horizontally with the curve and then I bring it down to the x-axis, the value obtained is 50, then 60, and a little before the mid. So it could be taken as 64. So this is the first value obtained against the value of 46 after first half-life. The next point is 32, and 32 is being shown by this box. So I make a horizontal line here, and then when I match this line with the horizontal axis, the value we get is exactly 130 hours. Okay, so the next point, 46, 32. The next point is 25, and 25 is in the mid of 20 and 30, so it is here. So when I match this point with the curve, we get a value which is in the mid of 190 and 200. So it is almost a value of 195. So these are the three values that we are getting: 64, 130 and 195. So I've written all the points here which we found from the curve, and now we would use these points in the form of pairs to find the half-life here. So the first half-life we can calculate here by subtracting the value of time. So 64 minus 0 gives us a half-life of 64. Then if we use the second and the third point, the value of half-life we get is 130 minus 64, 66 over here. And now I would be using third and the fourth point as a pair. So the value of half-life we get is equal to 195 minus 130, and it is equal to 65. Now to find out the final value of the half-life, we are going to average out these three values, and by adding them and then dividing by 3, we get a value of 65 as their average value. So the final answer for this part would be the half-life is 65 hours. So this is the procedure to calculate the half-life using the given graph. The next part says many of the points plotted in figure 10.1 do not lie on the best fit line. Explain why. The reason is that the radioactive decay is random in time, which means it is impossible to predict when a beta particle would be emitted. So there is no pattern in this emission. It is unpredictable. That is why the points sometimes lie above the best fit curve or the line, and sometimes they lie below the line. Okay, the last part of the question says a beam of beta particle traveling in a vacuum enters a region between two plates. One of the plates we can see is a positive charge carrier, and the other plate has a negative charge. One plate is negatively charged and the other is positively charged. Figure 10.2 shows the arrangement. On figure 10.2, draw the path taken by the beta particles as they travel between the plates. So when the beta particles would enter the plate, they would make a curve like this, and they would be bended towards the positive plate. Since they carry negative charge and negative is repelled by the negative plate and attracted by the positive plate, so they would be attracted towards the positive plate. So the question ends here with this part.
We try to explain complex concepts in simple language and with effective examples. If you liked the video and the way we explain the subject, consider liking this tutorial, commenting on it and subscribing to our channel and press the bell icon, so that you stay updated and get notified when we upload more videos. Thanks for watching.